Okay, let's look at another little theorem of calculus. And this technically is not a theorem, it's more of just a fact, but it's hugely important in establishing criteria for the other theorems, your mean value theorem, intermediate value theorem, Rolle's theorem, average value theorem. You need to know the difference between differentiability and continuity. And it is a fact that if a function is differentiable at x equals a, then that function must be continuous at x equals a. And the contrapositive of that statement is also true. When I ask people for the contrapositive, I very frequently hear this statement just in reverse. If a function is continuous, then a function is differentiable. And that is not a true statement because you have to remember that a continuous function could have a cusp, and a cusp is a non-differentiable point. And so just flipping the order is not the contrapositive. The contrapositive does flip the order, but you also insert nots into the statement. So the contrapositive is if f is not continuous at x equals a, then f is not differentiable. And I'll abbreviate that diffable at x equals a. So a function is not continuous means it is not differentiable. And if a function is differentiable, then you know that it must be continuous. And that is important to be able to make those connections. To show that a function is continuous, if a problem asks you to show that a function is continuous, you show that the limit as x approaches c of f of x is equal to f of c. That is your limit definition of continuity. Sometimes, based on how the problem is presented, to show that the limit as x approaches c exists, you have to show that the limit as x approaches c from the left is equal to the limit as x approaches c from the right. And then you would have to show that both of those are equal to f of c. Sometimes you're lucky and you can just do both sides of c in one swoop, but sometimes you have to do two separate sides from the left and the right. To show that a function is differentiable, it's really two steps. First, you show that f is continuous. Whoa, whoa, whoa! What just happened? Let's try that again. So start by showing that the function is continuous at x equals c. That's step one. If the function's not continuous, then you just stop because the function would not be differentiable if you know it's not continuous. But if the function is continuous, then to show differentiability, you also need to show that the limit as x approaches c from the left of the derivative is equal to the limit as x approaches c from the right of the derivative. And what that will do is show that the slope is the same on both sides of the point. If you look at it, if you show that a function is continuous, yet there's a cusp, then at that point, you'll see that there is a very drastic change in the slope on one side versus the other. However, if a function is smooth and differentiable, then if you pick any point, you'll see that the slope on both sides of that point is the same. And that's what part B is showing. So you want to show first that the function is continuous, and then if the function is continuous, you need to show that the slope or the derivative is equal on both sides of c. And if you meet both of those conditions, the function will be differentiable. So let's look at this problem. This is an old AP exam, I think from the 80s, but we have a piecewise function, and part A is asking you to find the value of k that makes the function continuous and justify your answer. The algebra behind finding k is not bad. If this were a multiple choice question, this would be very quick, because to actually find k, all you do is plug 2 in for x on both of these equations. 2 times 2 plus 1 must equal half of 2 squared plus k. You set the two equal to each other and you plug k2 in. What did I just say? You set the equations equal to each other and you plug 2 in for x on both of them. You'll get 5 is equal to 2 plus k, and we find out that k is equal to 3. So that would find the value of k. However, we have to justify that answer. And I guess I can take this over here. So there's the algebra for finding k. The calculus for justifying that is you've got to show that the limit as x approaches c is equal to f of c. And in this case, we will have to look at left and right sides separately. So I'm going to have to actually write down the limit as x approaches 2 from the left of f of x is, and the left side is this top one. That'll be 2 times 2 plus 1, which is 5. And then I'm going to find the limit as x approaches 2 from the right of f of x, which will be half of 2 squared plus 3, and that is also 5. And I need to show what f of 2 is. And when x equals 2, we're at the top, and the left side of 2 is at the top, and the right side of 2 is on the bottom. F of 2 is going to be 2 times 2 plus 1, which is also 5. Therefore, the limit as x approaches 2 of f of x is equal to f of 2. And I like to kill it dead and put the actual value they all equal, which means that f is continuous at x equals 2. And so there is your answer for part A. Part B is a booger. It says, using the value of k in part A, determine if the function is differentiable. We've already established continuity. Now we need to show differentiability. And here's the ugly part. They asked you to use the definition of the derivative. Whenever you see that phrase, they're telling you to use limits. You can't use derivative shortcuts to do this. We've got to actually set up that limit definition of a derivative and solve it that way. And remember, to show differentiability, we've already established continuity. We now need to show that the left and right sides of the derivative are the same. And we have to use the derivative, the limit derivative, which there are 2 methods to do that, but I'm going to use this one. The limit as x approaches c of f of x minus f of c over x minus c. That is the limit derivative I'm going to use. You could use the h approaches 0 method. I just think this one is a little bit nicer. So I'm going to have to look at the left side first, the limit as x approaches, and we're concerned about x approaches 2 from the left side, and it'll be of f of x. And if I'm doing the left side, it's that top equation, so it'll be 2x plus 1 minus f of 2, which we've already established is 5, all over x minus 2. Okay, well, that's going to turn into the limit x approaches 2 from the left. That's 2x minus 4 over x minus 2. You could lope this, but lope is actually going to be more work than just factoring. So I'm going to factor the 2 out of the top. We have x minus 2 on top, x minus 2 on bottom. The x minus 2's cancel. We are only left with a 2. So now I know that the left side of x equals 2 has a slope of 2. Now I need to check the right side. So limit as x approaches 2 from the right of f of x, which is half x squared plus k, which is 3 in this case, minus f of 2, which is 5, all over x minus 2. And we're going to do some algebra here. Limit as x approaches 2 of 1/2 x squared minus 2 all over x minus 2. If you factor a 1/2 out of the top, half times x squared is half x squared. Half of 4 is 2. And then you can factor that x squared minus 4 as a difference of squares. So limit as x approaches 2 of 1/2 x plus 2. It's doing that thing again. X plus 2, x minus 2, all over x minus 2. We'll cancel those x minus 2's. And now I can plug 2 in. Half of 2 plus 2 is 2. And now I can see that the limit as x approaches 2 of, from the left of f prime of x is equal to the limit as x approaches 2 from the right of f prime of x. Therefore, I'm going to do this. Let me erase that. And by part A, f is continuous at x equals 2. Therefore, f is differentiable. at x equals 2. And if it weren't for them forcing you into the limits on this one, it really wouldn't be as bad. You could use your derivative shortcuts, your power rule. However, they did say using the definition of a derivative, so that kind of forces you into this method. And if you didn't do that, you wouldn't get your points. All right, and then part C, they have changed the value of k to 4, and they want you to determine if f is differentiable and show the work that leads to your answer. Okay, well, right off the bat, I already know the answer is no. Because in part A, we established that f, in order for f to be continuous, k must be 3. Well, if we change the value of k to 4, we have now broken that continuity requirement, and this function will not be continuous. And if a function is not continuous, then the function will not be differentiable. However, we do have to show the work that leads to our answer. And to do that, I'm just going to show that this function is not continuous. So the answer is no, and I'm going to establish that by looking at the left and right side. The limit as x approaches 4, not 4, we're looking at x equals 2. X approaches 2 from the left of f of x is going to be 2 times 2 plus 1, which would be 5. The limit as x approaches 2 from the right of f of x, when k is equal to 4, is going to be half of 2 squared plus 4, which is 6. And if the limit as x approaches 2 from the left is not equal to the limit as x approaches 2 from the right, then the limit will not exist and f is not continuous. Therefore, f is not continuous at x equals 2 when k is equal to 4, and therefore not differentiable. And there you go, at x equals 2. So there is a good question that relies heavily on the continuity, proving continuity, establishing differentiability, and then making the connection between continuity and differentiability.